Back to the cosmos. Now we want to talk about formation of planets and eventually, of course, end up with our own planetary system. And the astronomers tell us that if you're going to make planets, the first thing you have to have is a star. So now we know how stars form. So out there and amongst all this cosmic dust that fills the space between the stars, a new star is created. Now, how it's created, I'm not really sure, except one thing I read indicated that perhaps it was the energy from a nearby supernova that resulted in the formation of this new star. So the picture I want you to have then, brand new star forms surrounded by cosmic dust. If you sort of picture this sphere of cosmic dust, then the astronomers tell us that stars, of course, rotate. It seems everything rotates in the universe. And I think that's how it generates the gravitational forces to hold everything together. But the star starts to rotate, and astronomers tell us that out from every star, there's a magnetic field. So picture this magnetic field then sweeping through this sphere, if you will, of cosmic dust. Well, there are things in the cosmic dust that are magnetic, and they're attracted by it, and they start moving along with it, and they get everybody else moving with them. And so picture as time goes on, this sphere of cosmic dust starts to rotate. And remember how the galaxy flattened out when we talked about the rotation of all those stars? The cosmic dust cloud does the same thing, and as a result, eventually you get down to the point where this original sphere of cosmic dust is now a disk of cosmic dust extending out from the equatorial regions of the star. Now, in addition to that, while all that was going on, there was another very important process going on. Coming away from all stars, there is an energy force called the solar wind. Now, this is not wind as you and I think of it. You and I think of wind as moving air. That's not what this is. What this is are high-energy particles coming away from the star. But the interesting thing is that energy does the same thing that the wind does. Remember the wind, what it does? It picks up light things like pieces of paper and leaves and blows them away and leaves behind heavy things like rocks and stuff like that. Well, in the case of the cosmic dust and this force coming out, the solar wind, it does the same thing within the cosmic dust cloud. It picks up the light things, remember, which now are those frozen ices, okay, and moves them out to the outer edge of this disk, leaving behind closer to the star the heavy materials, the dense materials, the rocks, the minerals, and the metals. And now out toward the outer edge, you still have some rocks and metals out there because they were there in the first place, but most of those ices now have been moved to the outside edge. So picture what you've got now. This disk of cosmic dust has been now segregated by density into the denser things closest to the star, the lightest things, the lower density things furthest from the star. Then what happens? Well, here's another thing I never could quite figure out, but anyway, the astronomers say that within this disk, little eddy currents start to form within the disk. And these eddy currents now, once they start moving, remember Isaac Newton with his gravity force, as things start turning in space, this force of gravity is generated perpendicular to the direction of motion toward the center of rotation. And as a result, these individual eddy currents now, as they start rotating, any cosmic dust within them starts to rotate and collapse toward the center. And so picture now, each of these little disks, each of these little eddy currents within the disk are now collapsing on themselves. The individual pieces of cosmic dust, which I guess are dust size, start to slam into each other, and the particles get bigger and bigger and bigger as this eddy mass collapses, and eventually they turn into what are referred to as planetesimals. Planetesimals are simply sort of odd-shaped pieces. Note, if close to the star, they would be made of rocks and minerals and things like that. Further from the star, they would be made of things like the ices, but they start slamming into each other, and eventually, down at the very core of this thing, down at the very core of each one of those eddy currents, there's going to form an object that's going to grow larger and larger as more of those things slam into it, adding to it as time goes on. And eventually, sooner or later, it gets to the point where it takes on a spherical shape. Now, I find this an interesting thing. Apparently in space, you have to have a certain amount of mass before gravity can mold things into a sphere. Think of the moon and Earth, they're all spherical. That's because there's enough mass for gravity to actually do that. There seems to be a certain amount of mass you have to have, a critical mass, if you will, under which the objects will simply be odd-shaped. Well, in this case, sooner or later, down in the center of each one of these little rotating masses, there's going to be a spherical shape form. And whenever that forms, now we have what is called a protoplanet. Now, note again now. In the protoplanets nearest the sun are going to be, or nearest the star, are going to be made of rocks and minerals and things like that. The protoplanets furthest from the star are going to be made of things like ices. Now, this process continues on as the little protoplanets go around the new formed star, sweeping up what remains of the cosmic dust, sweeping up what remains of the planetesimals. They are getting fewer and fewer in number, so the impacts now, the collisions of those things with these central bodies starts to drop off, and eventually they start to get to a size where now the crush of gravity once again is great enough that some of the gravitational energy being turned into heat sounds like the story of a star, but the interior of this thing is not going to get into the millions of degrees this time. We're only talking about getting into temperatures perhaps in maybe 2,000, maybe 3,000 degrees centigrade. But even at that, 3,000 degrees centigrade is high enough to melt any rock we know. So picture then this planetesimal. As things start to melt within it, now we have another density separation taking place within the planetesimal. Whatever happens to be the densest stuff of all is going to settle to the center and form a core. Then surrounding that dense core, layers are going to form, decreasing in density outward until the lightest material, the lowest density stuff, is going to be on the very outside. So now we have a different scenario. We have now a body that has a central core with layers of decreasing density outward. Once you do that now you have a planet. That's the big difference between a planet and a protoplanet. If you were to slice a planetesimal in half, the inside would be totally homogeneous. But if you slice a planet in half, now you see an interior core surrounded by these layerings. So anyway, now we have planets, and there's the big difference. Note the planets closest to the star are going to be dense planets. They're going to be made of rocks and minerals and metals and things like that have an average density of about 6 grams per cubic centimeter. The planets out furthest from the sun or the star are going to be light planets made of frozen ices, densities probably somewhere around 1. If you want an example of that, all you have to do is to look at our own solar system, because our own solar system is a beautiful example. So if you look at our solar system, first of all, let's talk about the cast of characters here. In our solar system, we have one star, which of course is our sun. And note again that it's a rather smallish star. This is a small, lightweight star. Then we have 9 known planets. Now I say known because it always has been thought that beyond our most distant planet that we know of today, there are other planets. We've always thought that. But within the recent years, there are some investigators who say they have found some out there. Now, from what I've read about that, maybe they have, maybe they haven't. But I assume someday they're going to prove that beyond our own solar system, our known one, there are indeed other planets. So there are 9 known planets. Then there are around those planets about 31 plus satellites, moons, if you will. We have 1 moon, Mars has 2 moons. Most of the moons, satellites, are around the outer planets. Now I say 31 plus, that number's going up all the time too. We're sending space vehicles out to those outer planets now, and we're seeing other satellites, smaller ones that we were never able to see before. Now we can see them because we got space vehicles out there taking high-resolution photographs and that. So we have 31 plus of those. Then what we have, let's see, the next one on the list would be the asteroids. The asteroids are these odd-shaped bits and pieces of rock that orbit around the sun. In numbers, they probably, well, they're about, they say 100,000 named or numbered ones. Undoubtedly, there were many, many more than that. Those are the ones we can actually see from Earth with earthbound telescopes, but there are others undoubtedly out there. So there may be millions of those things. And then the next little character would be our meteoroids. Meteoroids are sort of, to me, very mysterious things. They're made up of rocks and iron. The thing about the meteoroids that are different from everybody else is that everybody else seems to be in some kind of an orbit around the sun. Meteoroids aren't like that. They sort of roam through the solar community and don't seem to have any particular path to follow. And then finally, we have the strange agent, of course, of the solar system, which are the comets. There are about 100 or so named comets, and again, named implying that there are others we'll probably discover, and we are discovering more all the time. But these are simply, as we'll find out, just strange balls of frozen gases that are out there, and we'll get around to those. Well, the first thing I'd like to do, I'd like to talk a little bit about some of the inner planets. The inner planets each have something to teach us, mainly about Earth. I'm not going to say an awful lot about the outer planets because I really don't know an awful lot about them, and it seems they really don't have anything to contribute to our understanding of Earth. But let's take the innermost one, Mercury. Mercury, innermost planet closest to the sun, as you would expect, is probably pretty warm, and it is. Noontime on the equator. Noontime on the equator is about 450 degrees centigrade, which is pretty warmish, you have to admit. But midnight on the equator, it falls down, I think, to something like 170 degrees below 0 centigrade. The thing about Mercury is that it has the greatest range of temperatures of any of the planets. And the thing to learn about that, the reason why is because Mercury basically has no atmosphere. Any atmosphere that Mercury ever had has long since been blown away by that solar wind we talked about coming from the sun. What atmospheres do, planets like ours that have an atmosphere, the atmosphere constantly conducts heat from the sunlit side to the dark side. So the idea is that when the sun goes down around here, obviously it cools off. But one of the reasons why it doesn't cool off any further than it does is because you're constantly conducting heat around from the sunlit side all the time. And the denser the atmosphere, the more heat that you're going to conduct. Possibility of life as we know it on Mercury? I don't think so. Actually, the reason why is interesting. The reason why there is only one and only one absolute requirement of life as we know it, and that, of course, is water. Anywhere you can have water, or do have water, you can have life as we know it. Well, there is no water on Mercury. I think we're pretty safe to say that one. Venus, the next one out. Venus, now here's a planet all of you have seen. Well, if you live in the northern hemisphere, that is. Venus is the brightest star in the northern sky. Now, obviously, it's not a star at all. It's one of our sister planets. And the reason why it's so bright is because it's the planet that's completely surrounded in a thick cloud cover. What you see if you were to view Venus from Earth with a telescope, what you see is not the planet, but you're actually looking at the top of that layer of clouds, that thick layer of clouds. Now, clouds are really good reflectors of of light. Think about driving along on a summer evening and you run into a fog bank, how your lights come back at you. Basically, that's all fog is a low-flying cloud. So they're very good reflectors of light. So that's the reason why Venus is so very, very bright. Now, the interesting thing about Venus, temperatures on Venus, day and night, makes no difference where you are, about 485 degrees centigrade. Now, note that's higher than Mercury, even though it's further away from the sun than Mercury. Why? There has to be some reason. And the reason why, of course, is because of something we call the greenhouse effect. You all know that the greenhouse effect basically is this mechanism whereby the lower reaches of our atmosphere is maintained at a certain temperature due to the presence of greenhouse gases. Now, the greenhouse gas on Earth, it does most of the work, although it's not the best in terms of doing the job. Methane probably is the best doing the job of greenhouse gassing, but carbon dioxide is the one on Earth that does most of the work. Well, anyway, the carbon dioxide content of Earth's atmosphere is such that it has kept it at about, 15 degrees centigrade on the average over the long haul of geologic time. Well, it just so turns out that those clouds surrounding Venus are not the kind of things we have here. They're not water like ours, carbon dioxide. The Venusian atmosphere is about 95% carbon dioxide. So it's this super greenhouse effect that results in the temperature on Venus. We'll talk about Earth, of course, for the rest of the class. But the other one, Mars. Now, this is my favorite planet, Mars, the great red planet. And the reason why it's my favorite planet, this is the source of Martians. This is where all the space people came from. This is an interesting story. The first person to actually observe any of the planets, including the moon and all, up close and personal was Galileo. Galileo was the first person to use a telescope, actually, to view the heavens. He did not invent a telescope. I've read where he did. He did not. He just used it. But he was the first one to see the impact craters on the moon very clearly. He was the one to see the circles, rings around Saturn, although now we know they all have rings. But he was the one also that observed Mars. And what he saw on Mars were these grooves on the Martian surface, and he made note of that in his notebooks, but apparently he didn't really take it much further than that. But later on, there were two Italian astronomers independently studying Mars, and they saw these grooves on Mars. Matter of fact, they even made maps of them, and they published their work in Italian, of course. And in the Italian, they reported the presence of these grooves, and they reported in Italian that the Martian surface was cut by canali, which is in Italian, channel. Well, when they were translated into English, whoever did the translation screwed up. Because what they did, they translated the canali not as channel, but as canal, which it really did look like, I guess. Well, there's a big, big difference between a channel and a canal. Channels are natural features. Channels are carved by streams, for example. Every stream has a stream channel. Glaciers carve channels. Even the wind, in some cases, can carve a thing that looks like a channel. So these are natural things. A canal, on the other hand, is a ditch dug by somebody to move water from one place to another. As soon as the general population saw that, here was the proof. There are people up there. There are Martians. They really do exist. And it wasn't just the average person. Percival Lowell, who was one of the leading astronomers of the day, spent a lifetime and a fortune trying to prove it. Question: are there canals on Mars? No, there are no canals on Mars. Are there channels on Mars? Yes, there are channels on Mars. And that's what geologists are so interested in. There are channels on Mars. There is absolutely no doubt in any of our minds that the channels we see on Mars were carved by streams. These are stream channels. There are deposits that are stream deposits. There are deltaic deposits. Every indication is that the Martian surface once had water on it. It was not quite as much as we have. In other words, 70% of Earth is covered with water, the oceans. I don't think the Mars had that sort of water. Maybe they had huge, huge lakes, but nevertheless, water existed. What does that mean? That means they had to have an atmosphere like ours that was dense enough to keep the water from evaporating. They had to have an environment that would support life as we know it. That's the important thing about all that on Mars. That's why people are so interested in getting to Mars, is trying to find out what's going on or what did go on, because now there is no water on Mars. Oh, there may be some water underneath the frozen ice caps of the polar regions, but they're not ice now. The water ice, that's frozen carbon dioxide. Some people think there may be some frozen water ice deep within the soil. Maybe, maybe not. But the point is, the atmosphere disappeared. Once the atmosphere disappeared, it's like a vacuum. All the water disappeared too. Question: what happened? Answer: we don't know. And that's what's so interesting about Mars, is what happened to Mars. Because here we are, just right next door. What happened to Mars? Could it have happened to Earth? Possible. We don't know what happened anyway. So anyway, there's the 4 planets. Now these are grouped together now, and they're referred to as the terrestrial planets, because these 4 planets, Mercury, Venus, Earth, and Mars, all have things in common. First of all, they're all relatively small. Venus and Earth are about the same size, 8,000 miles in diameter. I think Mars is about 4,000, and I think Mercury is about 3,000 miles. But anyway, they're all small. Dense, the average density is about 6. So we group them together and call them the terrestrials. They're all made of the same stuff. So the things we're going to talk about, Earth being made of, they're made of the same stuff. Now, the outer planets would be Jupiter, Saturn, Uranus, and Neptune. These are the great, great gassy planets. These are the planets made of frozen gases or gases in one form or another. Now, these are huge planets. Jupiter, for example, is 90,000 miles in diameter. 90,000 miles. You could take all the other planets, roll them into one ball, and the ball wouldn't be as big as Jupiter. It's humongous. So these are very, very large planets. Being made of gas, of course, They're nothing like Earth, and I really don't know much about them other than that they don't really contribute much to our understanding. So we'll sort of leave the Jovian planets, although are the Jovian planets. That's what classified as the Jovians. Now, in between Mars and Jupiter is where the asteroids are, or most of them, I guess. What are the asteroids? Well, they're just bits and pieces of rock from what we can tell. They're just odd-shaped things, so they're not big enough to become spheres. I think the large one is something like 700 miles in long dimension, and even at that, that's not large enough to have the mass to be molded into a sphere. So these are simply odd-shaped bits and pieces of rock. The question is, what are they? Well, when I took my first geology course, and I was taught that what they were the remains of a terrestrial-type planet that was in the orbital between Mars and Jupiter that disintegrated. How? Nobody knows. Was it hit by something and just split apart? Possibly. Who knows what happened to it? But it disintegrated, which means what the asteroids are the bits and pieces of that once existing terrestrial-type planet. I don't think that's what they consider now. I think today what they consider these to be are planetesimals. These are planetesimals that were going to get together to form another terrestrial planet, but never had the opportunity. Why? Well, first of all, you had this humongous planet, Jupiter, right on one side, pulling them in that direction. On the other side, you had the sun and everybody else pulling them in that direction. And this tug of war between those two forces of gravity simply prevented them from getting together. So I think what they think the asteroids are now, they are simply planetesimals that would have gotten together had they had a chance, but never had the chance. Let's see now, the next one, meteoroids. Meteoroids, well, here's the first thing. There are three words, meteor, meteoroid, and meteorite. I always ask students, what's the difference between them? Question, what's a meteor? Well, a meteor is really nothing. It's just a flash of light through the sky. And what it is, it's either a meteoroid or a meteorite burning up as it plunges into our atmosphere. And then the question, of course, to be asked is which one of those is it? Well, it turns out as long as they stay up there, they're oids. Once they land on Earth, they're ites. So that's the difference between them. It's just location. Now, kinds. There are three basic kinds of meteoroids. There are the stonies, made of just, as it says, rock. There are the ironies, made of iron. And then there's the stony ironies, which are mixtures. Now, of the three, apparently the stone ones are by far the more abundant, most abundant. How do we know that? Collections made in Antarctica. Down there, you see they all fall into the ice, and then at the front of the ice, where the ice is melting away or sloughing off, they just go around and pick them up and just count them. It's just that simple. So anyway, the stonies seem to be the most abundant of all. We always want a question about impacts. Well, an interesting question that was asked to me one time was, why is it that you look at the moon, and here on the moon, only 238,000 miles away, all the impacts you see there are probably from meteoroids impacting the surface of the moon. Most of those are very, very, very old. We're dating back now to the primeval days when the planets were first being created, possibly even in that transition into the planetary stage. So they're very, very, very old. There are very few new ones. Well, the question was, why do we have all those on the moon, and here we are only 238,000 miles away, and you don't have any on Earth, or very, very few? Well, the answer is, back in those primeval days, we had the same number of impacts that they had. Now, the difference, well, the difference is, first of all, we have 70% of the area covered by water, so most of the things that fell in the ocean where you'd never see them anyway. But what about the land? Why don't you see craters on the land? Well, the reason why is one of the topics we're going to take up later on is weathering and erosion. Those two things combined, they're like big erasers, and they simply erase things, like mountains are erased by weathering and erosion, let alone craters. But the interesting thing is, now that we're up above Earth and satellites, looking down, we're starting to see faint outlines of old impact craters. It's like, for example, if you took a piece of paper and drew a circle on it with a pencil and then tried to erase it. Is it absolutely gone? No, you can still see the image of that circle. So the same thing is true here. There are images out there that we're now starting to see, and there are a lot more than we ever suspected before. The most recent one, the most recent impact of a meteoroid becoming a meteorite is, of course, Meteor Crater, or the Barringer Crater is the true name of the place down in Arizona. Here you have a hole in the ground. It's about a mile across, about 500 or 600 miles deep. This thing was estimated to have been caused by an iron meteor, or stony meteorite coming in, probably weighing about 250,000 tons, traveling at 25,000 miles an hour when it hit. And I always ask my students, remember now, this is about 50,000 years ago. 50,000 years ago, there were no human beings in the Western Hemisphere yet. So my question to my students are always, did it make a sound? And that's just sort of a philosophical thing you might think about yourself. Okay, so they have those. Now, the comets. The comets are, well, before we get to the comets, let's go back to one more of our planets. I want to take a little bit about Pluto. Pluto is the maverick planet. It doesn't fit anywhere in the picture. If it fitted into the picture, you see, it should be one of those large gassy outer planets, and it is not. It's small. It seems to be made of rock. We really don't know what it's made of because it's so far out there. All of our pictures are even very, very fuzzy. It was only discovered in 1933. Mathematically, as a matter of fact, it was located. But anyway, we don't really know much about it. Probably what it was, maybe a captured something from outer space, just came in at the right angle, caught by the gravitational pull of the sun, went into orbit around the sun. And nothing fits. The orbital isn't in the ecliptic where all the other planets orbit the sun. It's about 17 degrees to it. It has a huge elliptical orbit where all the others are almost, not exactly, but almost circles. Copernicus told us they were not circles. But anyway, it's so much different that today, recently, I read again where they're trying to downgrade it. They're trying to downgrade it from a planet to something else. I think the problem, however, is that it's been a planet for so long that I don't think they're going to do it. At least, well, stay tuned. We'll see if they eventually do downgrade it from a planetary status. Now to the comets. The comets are sort of strange, too. There aren't very many of them, well, named ones. There are about 100 or so named ones. And what they are, they were described by Whipple as being dirty snowballs. And I think that's a great description, a dirty snowball, because what he thought they were simply balls of frozen water ice. And the dirty part would be bits and pieces of rocks and stuff inside that dirty snowball. Now, if you think about that, that basically is the composition of the stuff out there at the outer edge of that disk when we talked about separating the ices from the heavy things. So these seem to maybe there's something to do with those outermost planets that formed way out there. Well, anyway, we really don't know, but that's the interesting thing about the comets. The other interesting thing about them, there seem to be two sources of them. One is called the Oort cloud. The Oort cloud was postulated by a Belgian astronomer by the name of Oort. He said out beyond our most distant planet, possibly halfway to the nearest star, which is, the star is 4.4 light years away, so this may be 2 light years out there, you have a belt of these things going around the sun. There are comets that apparently come off that and in around the sun, but you never see them again because the orbital period is so great. We think now that the ones we see are actually orbiting around the sun just beyond our own solar system, known solar system. They come in around the sun, and again, these huge elliptical orbits. And the interesting thing about them are their tails. People think the tails trail behind them. No, they don't really. The tail of a comet is generated as a result of that solar wind impacting the front face of that frozen ball of ices, vaporizing, ionizing them, driving them away from the sun, and then when the electrons go back, of course, they make it into light. So as the things go around the sun, through our solar system, that tail constantly swings around, eventually always pointing away from the sun, and when they're beyond the orbital of about Jupiter, the tail goes out. So it's only when they're in closer than about the orbital of Jupiter we actually have them. Impacts of comets. Pretty rare, pretty rare. The two I might comment on, at least we think both of these were, there was one that we think crashed into what is now the Gulf of Mexico about 60 million years ago, and that's the one that is reputed to have given the death to all the dinosaurs at the end of the Cretaceous period. That's still up for argument whether it really did or not. But that was it's been known now, it did indeed crash there. Whether it gave the demise of the dinosaurs is still of argument. The other one came down over what is now Siberia, I believe it was in 1912, And we're almost certain that it was a comet because it took about 20 years to get in or see the place. But when they got there was no hole, so it didn't impact the Earth. There were no bits and pieces of rock or metal anywhere around, and it wouldn't be, of course, if it was just frozen gases. And so that's what we think it was, an impacting comet. But other than that, the possibilities of being hit by a comet, pretty rare. You can probably get comet insurance really, really, really cheaply. So anyway, there's your solar system, and the next thing we want to go on is to what has to be the most significant concept ever set forth in the whole history of geology, namely plate tectonics. Stay tuned.